So the last thing I want to do when we talk about the countdown latch is show you an example application to illustrate how it works in practice. We're going to illustrate this using a kind of a fun program I've written, which you can download, which shows how to use the countdown latch as an entry and an exit barrier to control when a group of threads start to run and when those group of threads finish. The particular application is called the Greatest Common Divisor app. I've got a whole bunch of different variants of this. And what they do is this particular implementation uses a pair of countdown latches to coordinate the benchmarking of 4 different Greatest Common Divisor algorithms. And if you run this thing, you can see, if you look carefully, you can see it kind of does a bake-off with these different algorithms to see how long they take to run. You probably remember that GCD computes the largest positive integer that's a divisor of 2 other numbers evenly, so GCD of 8 and 12 is 4. I think you probably knew that already. This particular program tests 4 different GCD algorithms, and it turned out to be very convenient because I had a quad-core processor, so I could have one algorithm running on each core, so I could do a fair kind of comparison. One of the algorithms, which turns out to be really slow, is the GCD method defined by the big integer class, which is used for arbitrary precision arithmetic. And while you can support really arbitrarily large numbers, the GCD method is rather inefficient. There's also the iterative Euclid algorithm, which does Euclid's algorithm for GCD. That's probably the one you're most familiar with. There's also a recursive version of Euclid's algorithm that just does recursion instead of using a loop. And then there's also a really, really bizarre GCD algorithm that uses binary arithmetic, which works really well, I think, if you were to program this in assembly code. Not as efficient in Java, ironically. And so what we do is we run all these different algorithms, and we see which one works the best. And typically, in my experience, the GCD iterative and the GCD recursive Euclid algorithms are about the same. The GCD binary is a little slower, and the GCD big integer is really, really, really slow. But it turns out that the details of the algorithms aren't important. We don't really care. We're just using different ways to compare 4 things, and we want to make sure they all start at the same time. We want to make sure they all finish at the same time. So let's talk about how we actually do this. And you can find the program here in my GitHub account. So there's a test class that will test these different algorithms. There's a GUI version that runs them in a GUI, and then there's also a unit test version that runs the same algorithms in a unit test. I'm showing you the unit test version just to make it easier to see. It has less Android stuff. The first thing that we do is we initialize all the algorithms. We have a factory method that creates a thing called a GCD tuple, which keeps track of the algorithm we're going to perform. We create a new entry barrier, which is given the count of 1. We create an exit barrier, which is given a count of the number of tests we want to run. So let's say we have 4 algorithms. The count will be 4. We then go ahead and for each of the tests in our GCD tests, we go ahead and make a new thread to run that particular test. So, big integer test, recursive Euclid test, iterative Euclid test, binary GCD test, etc. We're going to make a new thread, and it's going to go ahead and this worker thread will be past the entry and exit barriers that we created up here. And then we're going to go ahead and start the thread to begin to do the computation. Now, we don't want the threads to start right away. We want them to kind of wait until we have the main program tell them to start. At least that's what we think we want to do. We'll see that the different variants support this with greater or less extent. So these threads are now up and running, but we don't want them to start yet. We're going to print starting tests, and then the main thread is going to say, okay, you other background threads, you can start to run now, because I've told everybody that the tests are starting. So we don't want these threads to start running until we've printed starting tests. So after we print starting tests, then we say anybody who is up and running can begin. So that means the worker threads can proceed. But this is a little bit weird, and you'll see this is actually a good motivation for the cyclic barrier that we'll talk about next. In this particular case, the main thread is saying, okay, you guys can start to run. However, we don't really know the order in which these threads are actually launched. So one of them might be launched right away. The other 3 may be a bit of a laggard. So after this countdown method is called, threads can start any point after that phase. But if one thread takes a long time to start, for whatever reason, other threads could have already begun to run before it gets a chance to start. So this is just saying, I've printed starting tests, but it's not actually preventing the other threads from running until they all show up. So in other words, the long and the short of it is that using the countdown latch as the entry bearer doesn't ensure that all the worker threads start at the same time or start their computations at the same time. It just means that once they begin to run, they can then proceed. Think about that. It's a subtle distinction, but we'll talk about that, especially when we get to the cyclic barrier discussion. We then have the main thread wait for all the other threads to finish. So this really does work perfectly fine. So this is an exit barrier where we're waiting for all the threads to finish, and this will not proceed until all those worker threads are done. And note that after a wait returns, we can't reuse this particular instance of the countdown latch without making a new instance. So we can't reset it. That's, again, distinguishing countdown latch from cyclic barrier, where you can reuse it, as we'll see. OK, here's the GCDCountDownLatchWorker class. This is the one that's actually going to be running. There'll be one instance of this for each thread. And you can see this is going to stash away the entry and exit barriers in the various fields. It also initializes other stuff like the actual algorithm to run. And then once we start the thread, the run hook method gets called back. So this run hook method is going to get called back. We want the run hook method to wait until the main thread says, OK, I've printed starting tests. So we don't want to run before then. But as long as the main thread is called starting tests, then this guy is going to be able to do the computation so that the await will return, and it'll run the test. Again, the key thing to note here is that the countdown latch doesn't ensure the worker threads all start simultaneously. It just ensures that a given worker thread starts after the main thread says countdown on this entry barrier. It then goes ahead and runs the algorithm that's associated with this object. We don't really care what it does. It just does some computation. And then the last thing it does is it counts down on the exit barrier on its way out. So when it's all finished, it says, hey, I'm done. And of course, that'll decrement the count by 1 atomically. And when the count reaches 0, then the main thread can go ahead and finish as well. OK, so that's the quick overview of countdown latch being used as an entry and an exit barrier. As you can see, there are some deficiencies with countdown latch in terms of ensuring everything starts at the same time. And so we'll discuss that when we talk about cyclic barrier next.